Hey guys, welcome to the first set of videos regarding the specific alkene reactions. So I've made this, I'm going to be making these specifically for the way that your exam one is going to be going, and that you're going to be omitting two reactions and you'll learn them after, well, two types of reactions that you'll be learning after exam one. And also, a lot of these reactions that you'll see in all the alkene reactions you'll see on practice tests and that you might encounter online will deal with something called stereochemistry and something that you may hear as syn or anti-addition. Disregard that because it's not going to be in your exam one. That's going to be exam two when you learn stereochemistry. Okay, and so these are going to be a little bit more simplified and tailored to your exam one. Okay, and so the way that I'm going to be doing these videos, and if you don't like my method of going through this, that's perfectly fine. It's whatever helps you guys. This is just the way I learned it when I was taking the class. Is I'm going to be splitting the reactions and grouping them into three pathways, three families. Okay, and so the first one is called a carbocation. Is going to go through a carbocation pathway. Okay, and I've also grouped a lot of these reactions within this and have simplified them down. And so I can show you one scheme that'll cover three reactions. Okay, and so let's start with the first reaction. So I'm going to draw some sort of an alkene, and I'm just generalizing here. With the R group can be any sort of carbon chain, doesn't really matter. And I'm going to draw, let's erase that. I'm going to draw HX, and X equals a chlorine, a bromine, or an iodine, not fluorine. Okay, you'll never see fluorine in these reactions. Okay, and so this is called a hydrogen halide addition of an alkene. And so a lot of people like to split these up into three reactions, one for each of the halogens I showed you. But the reaction works the same with all three. So why not just group them into one general reaction? So it's much easier to just show it this way. Okay, and so our arrows, how exactly are they going to look? Well, if you watched the previous videos and you saw a lecture, you know that the double bond is just going to reach out and grab that hydrogen. It's going to come in and grab that. The bond here breaks, and we're going to form a carbocation. Now remember, the more stable carbocation is what forms. So the more stable carbocation between this carbon or this carbon will be this secondary carbocation. So we're going to have a carbocation right there. Our hydrogen added over here, and we still have our halide right over there. And so remember, because this follows a carbocation pathway, rearrangements are possible. Okay, and so in this case, since I just wrote a general R group, I'm not going to show a rearrangement. I'll just give you an example right after this. But remember, carbocations, watch out for rearrangements before you attack with the chlorine. Or the bromine. Actually, so I should actually just draw this as a X. And that was my mistake. And so it's going to come in, it's going to attack my carbocation. So now we're going to have our hydrogen here and our halogen. Okay? And so let's just show you guys an example of where we can shift. Okay? And so I'm going to draw this structure here, reacting with AHX. And so our first arrow is the same. It's going to come in, going to attack that. So we're going to get a carbocation and a more stable carbon, the more substituted carbocation. And our halogen will be right there, or halide. And so if we look at the carbons adjacent to it, the carbon on the left, right over here, has a hydrogen over here. And if we move it, we'd have a tertiary carbocation. So we start the arrow from the bottom, and it goes to that carbon. giving us that carbon over there. Oh, and remember we added the hydrogen here, and a positive charge there. Now our halide comes in, attacks, and we're gonna get this answer. All right, and so always watch out for shifts for all carbocation preceding reactions. Okay. Now let's go on to the next set, and also just remember that X can either be the chlorine, bromine, or iodine. Remember, there's no reason that we have to split this up into 3 separate reactions when in general we can generalize it to this one little pathway. Okay, they all follow the same thing, whether I make it a HCl, HBr, or HI. Doesn't matter, right? And so let's go on to our next reaction, and this is going to be called an acid-catalyzed hydration. Okay, acid-catalyzed hydration. So I'm going to draw a molecule over here, and actually let's keep it consistent to what we had before. Okay, and so pay attention to the name. It's called an acid-catalyzed hydration. And so this reaction is going to use actually, sometimes you'll see it as 2, sometimes you'll see it as 1 reagent. So at the top, you'll have some sort of an acid. I'm going to write H2SO4, right? Yep, you could definitely see an acid like that. Doesn't matter which acid they give you. It could be H2SO4. It could be H3O+, like the hydronium cation that you guys are probably more familiar with. And it could be something like just H+, because the whole point of acids is that they donate protons, so they could just literally write a proton up there. And underneath the arrow, you'll see a ROH group. Now, here's the thing. The R can either be a hydrogen or an alkyl group, like a CH3, an alkyl group, right? So methyl, ethyl, propyl, doesn't matter. It can be any of them. A lot of people like to split this up into 2 separate reactions, but we can simplify this down to 1 reaction, and I'll show you guys how it will be the same for both. And so I'm going to redraw the H2SO4 just so we can have a hydrogen to pick from. Okay. And so the first step, the double bond grabs a proton, always the same in this reaction, and we're going to break it off. So we're going to form the more stable carbocation again. Here's our hydrogen. And so now that we also have an HSO4 minus, right? Now here's the thing. You guys probably haven't seen this yet before, but usually what's written underneath the arrow is called a solvent, right? These reactions take place in a liquid, and so the solvent is what it's going to be taking place in. And so we have this HSO4 minus, but because it's in this solvent of ROH, with the R being an H or an alkyl group, that ROH is literally everywhere. It's going to be here, 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 right? And so it can get to that carbocation much quicker than that HSO4 will, right? Besides that, HSO4 is actually minus, is also stabilized through resonance, but you don't have to know that. All right, and so that means that this ROH group is going to attack instead of the HSO4 minus. And also, remember, because it's a carbocation, it can rearrange, okay? I'm just showing it without a rearrangement. And so we have our ROH with 2 lone pairs on that oxygen. It's going to come in and attack the carbocation, and the rearrangement would have happened before if it could. So we're going to get this as our structure. And so if we look at formal charge now, the oxygen is going to have a positive charge. And so we can't just leave it like that, right? Even though it reacted, we can't just leave it with the positive charge. And so it's going to have to be deprotonated. And the way we show this is we just take another one of the solvent molecules, and that's going to come in and grab that hydrogen. And then this bond comes in and breaks, and our final answer is going to be OR, okay? Sometimes it's just written as OR instead of with that bond in the middle, but it's the same. You get the idea. And now, like I said, people like to split this up into two reactions. One where the R is a alkyl group, and one where it's a hydrogen. I'm going to show you guys why we don't actually have to do that. And when you're, let's say, writing this in your index card, generalize it to just ROH, and you'll have both reactions. Let's show it with water. I draw this structure here with, and I'm going to try to change up the acids and stuff like that, so you guys get a feel for what they could possibly show you. So they could write an acid as an H plus over H2O. That H plus is the acid that the double bond is going to grab. It's going to grab that proton. Or if they're talking strictly about water is going to be the solvent, they could even just write H3O plus. Because H3O plus, you have to know, is the conjugate acid of water. It'll dissociate into H plus and then H2O. Okay? And so you should know that, right? So if only H3O plus is given, you should know that it's really H plus over H2O. And always, write it on your index card if you think you might forget it. Right? You have it. It's a good idea to use it. And so I want to give us a proton to use. So I'm just going to write H plus H2O. So the double bond is going to come in and it's going to grab that proton. We're going to form the more stable carbocation. So if you want to pause and quickly do it yourself, it's going to end up right there. And here is where our proton ended up. And now we're going to use our H2O. And then the double bond, one of the lone pairs is going to come in and attack that carbon. Now remember, if it could shift, it would, but the tertiary carbocation is surrounded by a secondary carbon and a primary. So that's not going to give us anything more stable. And so now we're going to get this structure, a positive charge, and we take a, oh, I wrote an OR there. Sorry, OH. And so now we're going to take another one of our little waters, right? It's the solvent, to come in, and it's going to deprotonate that. So now we're just going to be left with this is our final answer. And also on the side, we had this now. Now you don't have to really show what happens to the thing that deprotonates it. They don't usually care. Unless it's one of those mechanism questions, then they'll probably show you what it resulted in, just so you're not, just so it's clear what happened. Okay, and so if we look at the difference between what I just showed you and the above reaction, is we added an OH and before we added an OR. But I wrote here that our ROH group can either be an H or an alkyl group, right? And so the reaction ended up in the exact same way. The only difference is if I had an ROH instead of H2O, and instead of, like, an example of an ROH group could be this right here, right? If we had that H plus over CH3OH, we would just change this to CH3, okay? Because on the water over here, when I'm looking at this, it didn't matter which hydrogen we deprotonated. They're equivalent. When we had this step over here, with the right over here, we could only pick one hydrogen. We can't deprotonate in our group or a carbon chain group off of it. That's not how it's going to work. The hydrogen is a much better target, and so it's going to take the only available hydrogen, whereas here we only have hydrogens, and so the reaction works exactly the same. And so when I write my index cards, when I did write my index cards, is I just wrote ROH, and next to it I wrote R can equal an H or an alkyl group. And so with this simplification, we turned two reactions into one reaction. And up here, we turned three hydrogen halide addition reactions into just one reaction. Okay, so this is how I like to approach these carbocation reactions, or all these alkene reactions. I simplify them, and yeah, this is how I like to do it. So if you do not like this method, of course, feel free not to use it. Always, you can talk to the TAs. They've had their own tips and tricks from when they studied for these tests. Okay, and so in the next video, we'll be covering the next two family of reactions. Okay, and remember, carbocations equal the possibility of shifting. This is the only family of alkene reactions that will allow you to shift. The next two that I'm going to be showing you have no shifting, and so we can only happen here. And the same thing for the ring expansion. It's considered a shift, and therefore it only occurs with these reactions I showed you here, right? It's not going to occur with any of the other ones. All right, and so if something here didn't make sense, again, please feel free to talk to a TA. Yeah, and they will be happy to help you guys. And so I will see you guys in the next video.